So this video is going to be about a phenomenon called simple harmonic motion, and this lecture starts our unit on waves. So this is one of the last units that we're going to be doing in physics this year. So before we get into waves though, and sound and light and all the other cool stuff, we're going to talk about kind of the basis of it, and that would be simple harmonic motion. So we'll be returning to these ideas in the coming weeks. Let me see if I can. Okay. So first of all, let's talk about the cause of simple harmonic motion. So simple harmonic motion occurs when things oscillate back and forth. Okay, and one of the key features of it is that the oscillation is stable. So that means that there's some minimum energy, there's some equilibrium position that the object wants to kind of go back to each time. And so as it's swinging or it's bouncing, or orbits do this as well, there's a constant return to this equilibrium position. So we see here with the skateboarder right here, he goes up, but down here, like in this section right here, is going to be the equilibrium position. So he's always going to be returning to this spot. Okay, when you have a situation where you have an oscillation, but it's always returning, it's stable, and it's always returning back to the same spot, you're going to have simple harmonic motion. By the way, I should mention this because I'm going to use this a lot. I don't want to write out simple harmonic motion all the time, so I'm just going to abbreviate it SHM. All right, so when we talk about simple harmonic motion, there's three terms that come up a lot, and those are period, frequency, and amplitude. So when we talk about the period, you think of something oscillating back and forth. It's going to take a certain amount of time to get through one cycle of the oscillation. So that time is called the period of oscillation, and very often the unit for this is going to be in seconds. Okay, so very often we use seconds. You could honestly use any period of time. If you hear like revolutions per minute, RPM, that minute is going to be what that period is going to be measured in. Okay, amplitude. So amplitude, if you go back to the skateboarder here, the amplitude of his oscillation, go back one, would be this maximum distance that he gets away from my equilibrium point. Okay, so the amplitude essentially is how far it's swinging or how far it's oscillating. Okay, and so this will be in meters. But again, you can use any unit of length for this oscillation. And then we have frequency, and this one's a little bit trickier. So this is related to the period, whereas the period tells you the time it takes to complete one oscillation. So that's going to be in seconds. What the frequency says is how many oscillations you're going to make per unit time. Okay, and this is going to be the reciprocal of the period. So the frequency, which we'll abbreviate as F, is going to be 1 over the period. So very often we use a big T for period, and then this F will be in frequency. Okay, so whereas the period's in seconds, the frequency will be in 1 over second, and if we're going to be cool, we'll say seconds to -1. And the unit that we use for that is hertz, or Hz. So you're going to see hertz a lot when we talk about frequencies. So the frequency is the reciprocal of the period of oscillation. The period's the time for it to go back and forth one time. The frequency is how many times to go back and forth per second, usually. Okay. All right, so when we make a graph of simple harmonic motion, we can see things oscillating. But if we want to plot it out, position versus time, it's going to look very much like a sine wave, and we model it as a sine wave. And now I think you kind of see why simple harmonic motion is related to wave motion. So we have time on our horizontal axis going along here, and then say that this is going to be position. Okay, so position is going to be on this axis. Now the amplitude will be the distance from the equilibrium position. Our equilibrium position is this line right here. Okay, so this distance is going to be my amplitude. Okay, so that's my amplitude. From the top of this to the bottom, and then again, you can also go from the equilibrium position on down. Okay, so like right along here, this would also be the amplitude. So this distance is my amplitude. Now, as far as time goes, if we imagine it's going to start off at equilibrium, it's going to swing one way, it's going to go back through equilibrium, swing the other way, and then it's going to come back to equilibrium. So that this entire sine wave right here, so that whole distance, okay, this time is the period, the time it takes for it to do one oscillation. And then the frequency would be how many oscillations it made in a certain amount of time. Okay, so very often for simple harmonic motion, we'll represent that with these sine waves or with the cosines, possibly. Usually it's a sine wave just by convention. But that's how you can kind of interpret these graphs and how you can find the amplitude and how you can locate what the period of the oscillation is. Now, when you think about it, it's oscillating back and forth. The reason why it keeps on returning or trying to return to this equilibrium point is because that's where there's a minimum of potential energy. And we've come across this type of motion before earlier in the year when we talked about springs. So I have a spring system here, and the equilibrium position is about right there. Okay, so it's kind of oscillating. So the amplitude would be this distance that it gets, so this maximum distance it gets away from the equilibrium, but it's kind of oscillating back and forth. And so when it's at this maximum amplitude, it has all this potential energy, but it's going to keep on returning to this equilibrium position where it has zero potential energy. So this is position C, and all this potential energy will become kinetic energy. It's going to swing back, then the potential energy increases again, but it's always going to be oscillating around this point of zero potential energy. And so there'll be this constant conversion of energy from kinetic energy to potential energy, and then back and forth and back and forth. Okay, and that's a characteristic of simple harmonic motion. So in the next two classes, we're going to be studying two systems that are kind of exemplars, really great examples of simple harmonic motion. The first system is the pendulum. So in the pendulum, our equilibrium position is going to be at the bottom, and we're going to be swinging up, and this kind of distance that swinging would be the amplitude. And it's going to be swinging back and forth, and we'll look at how we can find the period and what the period depends on for a pendulum, like the time for one oscillation, what that depends on. And then we'll also look at springs and what the period of oscillation, the amplitude, and so on and so forth for a spring oscillating back and forth are. Okay, so that's a little preview about what's to come. In the next class, we'll review some magnetic fields and force stuff, and then we'll talk about some of these concepts and do some practice.